The Langlands program is one of the most powerful unifying frameworks in modern mathematics, connecting seemingly unrelated universes through invisible forces of symmetry. It links the discrete, invariant world of number theory, the arithmetic structures, with the transformative, continuous realm of harmonic analysis, the automorphic structures. Mathematicians typically view this as horizontal unification, the process of discovering profound mappings between mathematical territories that have already been formed. This diagram outlines the current standard for unification. It treats these domains as structurally independent at their origin, represented by these separate floating platforms. In this view, correspondence is a mapping discovered after the mathematical territories are already established. The bridge is an external construction. Horizontal unification successfully maps the terrain, but it assumes the independent existence of the very structures it seeks to connect. This leads to a foundational anomaly. If arithmetic and automorphic structures are truly independent at their origin, why do they correspond? As shown here, if these domains were truly separate, their deep equivalences would be a surprising accident, a set of coincidences requiring post hoc technical bridges. Unification appears as a series of improbable accidents, necessitating external mappings to resolve the mystery. The Lilien Thesis proposes an ontological shift to solve this anomaly: vertical unification. This comparison highlights the transition. Instead of moving across territories, the inquiry moves downward to investigate the generative substrate beneath the domains. Arithmetic and automorphic realizations are distinct expressions of one shared closure condition, as shown in this glowing root system. Correspondence is the inevitable downstream expression of a shared generative origin. To find this origin, we must look at the ontological void and ask what minimal conditions allow any mathematical structure to emerge. This visual defines generative closure as the absolute prerequisite. It is the minimal requirement for a generative process to stabilize into a persistent identity, providing a boundary to hold together. Where closure fails, no stable domain appears. Closure precedes structure. A boundary alone is insufficient. The structure requires an internal safeguard to prevent it from collapsing upon its own birth. This meshing of gears represents coherence, the internal safeguard of stability. Internal relations must maintain compatibility. They must preserve the structure's existence rather than negate it. Without coherence, internal relations violently repel one another. The entire structure shatters into dust before the mathematics can fully form. Mathematical reality emerges through this joint dynamic. Closure provides the boundary, and coherence sustains the structure from within. Once closure and coherence are satisfied, a single generative source can manifest through diverse mathematical modes. This prism illustrates the principle of multiple realization. A single beam of generative closure splits into geometric, analytic, and most importantly, arithmetic and automorphic realizations. The arithmetic realization highlights discreteness and structural invariance. The automorphic realization reveals the capacity for transformation and harmonic expression. These distinct realizations arise from the exact same generative closure condition. They are inextricably bound together by their shared common source. The domains of the Langlands program are complementary, coherent expressions of the same underlying origin. Complex mathematical phenomena, typically treated as independent technical rules, are actually the inevitable symptoms of this deeper unity. This representation describes duality as closure complementarity. Duality occurs when a single realization cannot exhaust the closure condition. The source expresses itself through complementary, mutually necessary forms to disclose its full architecture. This connection defines functoriality as structural memory. Functoriality is an ontological necessity. Transformations between realizations must preserve the underlying closure, or the correspondence would dissolve. This diagram explains representational incompleteness, the reason the Langlands conjectures resist exhaustive proof. No single formal system can capture the whole source. Conjectural persistence indicates vertical ontological depth, as arithmetic and analytic languages reveal only one manifest aspect at a time. The complementarity of duality, the preservation of functoriality, and conjectural resistance are the inevitable structural traces of a shared generative origin. This entire architectural theory can be distilled into a single rigorous formalization. This notation represents the generative correspondence formula. If a closure condition C admits two or more coherent realizations R, those realizations are necessarily constrained by their shared origin. This result establishes that a correspondence relation must exist among all coherent realizations generated by C. A Langlands type correspondence is a mandated mathematical constraint, the visible trace of this generative formula in action. The journey concludes where structure becomes possible, in the vertical depths of the generative origin. Correspondence is generated from the beginning of formal mathematical existence, inextricably linking these domains as they emerge. Steady, conclusive. Mathematical unification is the disclosure of the generative source beneath mathematical structures.